This video is supported by the National Science Foundation.
Hi, my name is David Kobler, and I'll be introducing you to integrated circuits. Integrated circuits can be found in various electronic devices we come into contact with every day. You have integrated circuits in your smartphones, in your smartwatches, and maybe even in your toaster. You will realize that they form a key component of our daily lives, and without them, we may never have any computing done. The questions we'll seek to answer in this module are: what are integrated circuits? How are integrated circuits used? How are integrated circuits made? And what are the components of integrated circuits? We may not answer these directly, but you will find that throughout the module, these questions will come up and will be taken care of as we learn the various aspects of integrated circuits. But before that, let's make sure we know what integrated circuits look like. Integrated circuits, in this case, can be square with various pins surrounding them. The pins you see allow it to connect with the circuit board. Integrated circuits can also have rectangular shape, as you can see. The cross section you have in front of you has the die exposed with the plastic case removed. You can also see the wire bond and some pins. The next one is a cross section of a real integrated circuit, and you can see its die as well as the pins sticking out from the bottom. As I said earlier, these pins allow it to connect with the circuit and communicate. So now, what is an integrated circuit? I need to mention that integrated circuits can also be called ICs. So during the lesson, I may refer to integrated circuits as an IC. An integrated circuit, or an IC, is a collection of electronic devices combined as a single unit with interconnections built up on semiconductor material. Notice that I have underlined and boldened keywords: electronic devices, single unit, interconnections, and semiconductor material. These are the keywords that you will need to keep in mind when you want to describe an IC. So throughout this lesson, I will point out these specific keywords and help you understand them. Let's start with electronic devices. Electronic devices can come in two separate categories. The first one we'll describe is the active device. Active devices transform or inject power, current, or voltage into a circuit. You can see the various examples of transistors, as well as transistors installed on a circuit board. Voltage and current sources also count as active devices. You can think of them as batteries, like what you'd put in your PS5 controller. The next category would be the passive device. Passive devices use the power or energy or current or voltage placed into the circuit. You can see the resistor, for example, which restricts the flow of current, the capacitor next to it, which stores charge based on current flowing, and the inductor, which stores energy in its magnetic field. They can also find their way on circuit boards and come together as the various devices that we will need for a successful circuit operation. Now that we know the types of electronic devices available, let's delve into the transistor to IC pipeline. We need this knowledge to understand the single unit and how it operates. Our single unit is composed of transistors. Transistors in today's technology can number in the millions on just 1 square millimeter. In fact, the A16 chip that Apple released recently and can be found in some of the more recent iPhones has about 14 billion transistors per square inch. If you want a good description of a transistor, think of it as a faucet. Now, the transistor, as you can see, is made up of a source, a gate, and a sink. The source would be the water company. The gate would be the knob that controls the faucet, and the sink would be where water flows into. So if the gate, which is the knob, is turned on, water or electricity will be allowed to flow. If the gate is turned off, water or electricity will not be allowed to flow. That is the simplest way of representing the way the transistor operates. This is important because this is the very basic interaction that allows us to send commands throughout our electronic devices. Whether you press a button or send a voice command nowadays, you require signals being transmitted through electricity like this that is transmitted via transistors. A group of transistors combined come together to form a gate. The gate would be the logic operation that a specific device requires. A group of gates come together to perform a specific function. For example, you can see that the NOT gate inverts the inputs that it's given, where a 0 becomes a 1 and a 1 becomes a 0. There are also different examples of gates available, including AND gates, OR gates, and XNOR gates. The group of gates come together to perform specific operations as a logic block. These logic blocks can be configured to do specific things based on the gates available. Once you have several blocks available, we can create a full IC, as you can see. So the transistor, in its most basic form, is allowed to come together to form a gate. A gate creates a set of logic blocks, and the blocks create the IC, which is the single unit that you see and can use. Now that we know our single unit, let's delve into our interconnections. Our interconnections are the wiring system that connects transistors and the other components on the computer chip. Interconnections are important because they allow for the passage of signals across millions of transistors. In fact, the limiting factor when creating ICs used to be transistor speed. But nowadays, it's the interconnects. Did you know that interconnects can number, when lined up, 30 miles of distance in one IC? Interconnects used to be made primarily of aluminum a couple of decades ago. It wasn't until the late 90s that manufacturers switched to copper. After all, aluminum was cheaper, malleable, and easy to find. It was used to create several interconnects for older ICs. As I said earlier, copper is the more favored material because it's a better conductor of electricity, it uses less energy, and requires narrower dimensions. Although the manufacturing process had to change for ICs just because of the switch from copper to aluminum, copper has continued to reign as the favorable material for interconnects. Now that we know our interconnects, let's get our understanding of semiconductor materials. Semiconductor materials are crucial components in electronics. They occupy that unique position because semiconductors have conductivity right between actual conductors and insulators. The most common semiconductor you will see is silicon. Silicon is a metalloid distinguished by its atomic number of 14 and the chemical symbol Si. It's abundant just because sand is everywhere, it has a stable crystalline structure, and is well suited for many semiconductor applications. Making semiconductor silicon wafers requires a lot of specific processes. The journey involves meticulously layering various materials, conductive, semiconductive, and insulating, to construct the transistors that you see. The layering is able to create a very complex circuitry that is really essential for the chip's functionality. Notably, the interconnectedness of these components is facilitated by the interconnections that you see in the previous slides. This intricate network plays a pivotal role in creating the functionality that you see. Modern technology is a marvel, and we can go from simple grains of sand all the way to the chips that we see in our electronics and devices throughout our lives. In fact, without silicon, we would not be where we are technologically as a race or as a species. And so now that we understand the place silicon occupies in the various processes that go into electronic devices, let's conclude our lesson for today. We understand that ICs are electronic parts composed of semiconductor materials like silicon. They are made up of multiple transistors connected through a network of metal interconnects made of copper. And they have increased in size and complexity over time, primarily due to us being able to reduce the number of transistors. But like I said earlier, we still have to deal with the issue of interconnects. Thank you for joining me on this journey. We will move on to the next set of slides. I look forward to seeing you again.